It's a great pleasure to be here tonight on this great occasion and to introduce my colleague and friend John Huth, who has done this, has led the way, so to speak, in showing us about the history of navigation and puts it to practical and anthropological use. I think it's a terrific opportunity for us in the collection of historical scientific instruments to make contact with this terrific subject. It's something that we have richly represented in the collection, our navigation and measuring devices for understanding the mapping of the world are some of the key parts of what we have here, and it's just terrific that John and the team from HMSC has been able to put it to such good use. John is the Donner Professor of Science in FAS at Harvard, and he is a terrific experimentalist in particle physics. He's somebody who co-directs the program of interdisciplinary science and innovation work at Radcliffe. He did his BA at Princeton and his PhD in physics at Berkeley. He's a major force in the community of the physics of particles and a terrific colleague, and it's a great pleasure to have him here. John.
Well, thank you for the kind introduction. So let's see, I do want to personally thank Sammy and Jennifer, Jane, and Janice, who I saw somewhere back there, who did a huge amount of help. There is, yeah, they're pointing at each other in getting this together. Can you hear me on this microphone? Yep, okay. And also some of the people with the collections that were incredibly helpful. Joseph, I see Sarah there. Carrie, is Carrie here by any chance? No, okay. And Diana. So it was wonderful to have them open up the doors to the collections and be able to root around in the closets and see all the good stuff and say, yeah, I want one of those and I want one of those and that kind of thing. So that was great for me. So what I'm going to do today is talk about some of the details of some cultures of navigation that may be unfamiliar to you, and you'll see some examples of these up in the exhibit. And one of the things that I found, and I'm not going to give you the details, you might want to ask me about this later in the reception, how I got into this. I got into this as the result of a kayaking accident. But I also found that there was this kind of prejudice towards, I guess, indigenous cultures having this mentality that they could find their way, and us poor Westerners couldn't. And many cognitive psychologists and anthropologists would say that Westerners were basically clueless in one way or another. And what I found, I proved to myself, was that you can develop these skills on your own. It's not like you're just helpless. We have the same mental apparatus as other human beings do. And so I hope to sort of give you an introduction to the way people in different cultures thought about their environment and how they used environmental clues to navigate. So one of the first tests I do with a group like this is, I do this all the time, so don't worry, and you aren't going to get graded on it. But I want to get a sense for how well people know their surroundings, how well oriented they are right here and now. So I'll tell you what it is, and you can't, don't look around and bias everybody, okay? Okay, so just look at me, okay, eyes front. And here's what I'm going to ask. I'm going to ask you to close your eyes, and when your eyes are closed, I'm going to give you a cardinal direction, east, west, north, or south. And then I'm going to ask you to point in that cardinal direction, okay? And hold your hands out, your finger, like this, okay? Like that. And then hold them, and then I'm going to tell you to open your eyes and then look around at the crowd, keeping your hands extended, okay? So is that simple enough? So think about it for half a second. Okay, close your eyes. Okay, point south. Okay. Now, open your eye, keep your fingers out, open your eyes and look around. Okay? Okay. So now, if you were to just do a vote among people, you might be pointing a different way. If we were going to do a vote among people, which way is south? by counting how many people you saw around there. Okay, so I would say the majority were pointing that way, which turns out to be correct. So typically what I find when I do this with an audience of so-called Westerners, quote unquote, is that about 65-75% will actually point in the direction that I call out. And so already you hear anthropologists or cognitive psychologists say that, no, basically Aboriginals in Australia have this uncanny sense of direction and Westerners don't, but we just proved sort of by voting that that's not really true. So what I have found is with my students in my class is that even if you pointed in the wrong direction, if you work at it for a while, you can become attuned to clues in your environment that you can use to orient yourself and find your way around. And if you do, you actually find that your sense of the world has kind of increased. You're actually more sensitive to the position of the sun in the sky or stars in the sky or the wind, that kind of thing. So what I'm going to try to do is just give you a few examples of that. But first, I want to talk about the universals in our mind. So how do we organize our space? There was thought that there were two possibilities. Around 1948, a psychologist named Edward Tallman tried to investigate this with classic rats in the maze experiment. So you can imagine there are two ways of doing it. One is what's called route knowledge, where you know a set of trails or roads and their intersections, but that's more or less it. Kind of a one-dimensional, quasi-one-dimensional way of visualizing your space. On the other hand, there's a possibility of survey knowledge, which is knowing an environment as if you're hovering over it and looking down from a magic carpet and you can see everything in 2 dimensions plainly. And then the question arises, how would you distinguish in a behavioral sense between whether somebody has in their mind route knowledge or survey knowledge? Or how would you can't ask a rat, but you can put a rat in a maze and see how they work. Well, it turns out that shortcutting is the behavioral clue that might indicate people would have survey knowledge as opposed to route knowledge. And so let's say you're down here. This is actually a route knowledge map of the Harvard Square area. So say you're down here and you want to get over there. If you only had route knowledge, you would go in along this familiar corridor, hit this node, and then go out again to get to that point. But if you were walking and you said, well, I want to get over here, you might think, well, it's silly to go all the way in. I want to just cut across. And so you would cut across that way along a street that would more or less lead in the proper direction. And I do this, I bicycle commute in and out of Newton all the time. And so frequently I'm taking shortcuts and trying to optimize my way there. Now, what you'll find is that when people are in an unfamiliar environment, they'll have route knowledge, but as over time they explore their environment, they'll start to learn how to do shortcuts. So this is true for mice, for rats, for dogs, and for humans. For most mammals, we all have survey knowledge when we know an environment reasonably well, and we'll have different maps for different locations, like where we grow up. I have this problem that I call the waking up in a hotel in the middle of the night problem, because it's dark and you wake up. I don't know if anybody else has experienced this, but sometimes I think I'm at home and then the room spins around and everything falls into place. And so that's because my brain is trying out different cognitive maps. Now, recently, there's been a lot of progress in the neurosciences in understanding the origin of cognitive maps. And this work was actually the subject of the recent Nobel Prize in Medicine in the fall. Around 1970, a researcher named John O'Keefe, studying rats, looked at a place in the brain, deep inside the brain, called the hippocampus, which is also the area responsible for future actions, imagining, and also episodic memory, memories you can call up at will, but also the site of something called place cells. And so he would put electrodes into the brains of rats and let the rat explore an environment and find that an individual cell would fire when the rat was at a single place in its environment. So I'm here, one cell fires. I go over here, that cell is now quiescent, and another cell fires, and so on and so on. More recently, there was a group in Norway, Edvard and May-Britt Moser, who looked in a neighboring region called the entorhinal cortex. So if you want to know where these things are in a rat, here's the hippocampus, and the entorhinal region is down here. And in humans, here is the hippocampus, and the entorhinal region is down here. So what they did was they looked in this region, and they found, much to their amazement, that there was a kind of cell that fired when the rat was in a particular set of positions in its environment. So the environment, in a sense, was tiled by these cells called grid cells. And they're called grid cells because this is an actual map of an environment a rat explored. And looking at a single cell, the single cell fires in multiple locations in that environment. So you can imagine looking at the floor of a bathroom and the tessellation of tiles and the intersection of the tiles. So you're at one intersection and this given cell fires. And then you move over to another intersection and then the same cell fires again. And then you shift everything over just by a little bit and you have another tiling of the environment and another cell encodes for that. Now we don't know exactly how the interactions with the grid cells and the place cells encode for this cognitive map, but we do know that there are multiple cognitive maps that get downloaded. You even have cognitive maps when you dream. So we've seen rats when they're in a dream state and they'll have a different activation in the hippocampus. If you're traveling differently, you'll have a different cognitive map, and that presumably has to do with scale and your ability to imagine landmarks. So it was mentioned that I'm a Radcliffe Institute member, and we have an ongoing series at Radcliffe of a set of lectures, some of which will still be coming up. Let me check the website. We also had a symposium on navigation in November, and one of the speakers was a woman named Eleanor McGuire, and she's best known for her work with London cab drivers. So she would take London cab drivers and put them in an fMRI machine. This is basically a machine that measures blood flow to specific parts of the brain that get activated. And she would give the cab drivers a virtual environment to navigate, and would find that the hippocampus would light up in the cab drivers, and would also find that the cab drivers had much larger posterior regions of their hippocampus than normal individuals. So there was a kind of weightlifting, if you like, going on where the hippocampus gets enlarged by using it a lot. Now, one of the more recent things that Eleanor has studied is the role of another region in the brain, which is known as the retrosplenial cortex. That's also in the limbic system, but it's somewhat distant from the hippocampus. And what this seems to encode is the permanence, a sense of permanence of landmarks, probably a sense of permanence of other things, but landmarks in particular. So here are things that you might consider permanent landmarks, a phone booth, a fire hydrant, and so on. A non-permanent landmark might be a bus or a pile of trash or something like that. What she found was that people who are good navigators, she would basically cluster people into good and poor navigators by having them negotiate a virtual environment. And then once she did that, she would then see how well they could identify the permanence of certain things. And what she found was that the good navigators had more activation of this region, this retrosplenial cortex, than poor navigators. And here is the data. This vertical axis here is just the amount of lighting up of the retrosplenial cortex. This is the hippocampus. So somehow when a person is engaged in negotiating an environment, these two areas will light up in an fMRI machine, and the good navigators had more of a response in the retrosplenial cortex. Now what's interesting when I hear about this stuff is I start applying this to my own life, and I remember that I was driving from a movie theater with my daughter and one of her friends across Newton, and anybody who has driven in Newton knows that the streets are incredibly higgledy-piggledy. Well, they're higgledy-piggledy here too, and always a little bit confusing. And I guess my daughter wanted me to take one of her friends home, and I had to quickly do a route in my head that I was going to take to get to his house. And then he said, oh no, I know a shortcut, you have to go this way. So I took another route that I knew. And so what was happening in a sense was I was taking this two-dimensional hippocampal map and then figuring out a route and figuring out a set of landmarks along the route, and then I would just follow those and check those off. Okay? So I was sort of looking at my brain in action in some sense because I've been informed by all of these studies. But then I got to an intersection, and all of a sudden I was dismayed because I thought I was at the wrong intersection, and temporarily everything sort of spun around and I didn't know where I was. What had happened was, since the last time I'd been at this particular intersection, and that time somebody had put one of these little bicycle signs and double chevrons to say it was a bike route. And so the permanence kind of had gotten erased temporarily when I looked at this one thing. And so, I thought, oh, that's what's going on. And so all of a sudden, what was sort of an academic topic became very real at that given moment. So we all have the same apparatus in our brains, but we may or may not use it to a greater or lesser extent, but it also points to the possibility that if you're a poor navigator and you want to become a good navigator, there's certain things that you can do. Now, Peter alluded to this anthropological aspect, and I'm going to dive into that in just a second, but I just wanted to sort of set the stage and say that we all have the same neural wiring for navigation. It's a question of how we use it, how we learn it in different environments. And as an intermediate stage, before I start to talk about specific cultures, I've noted that there is this phrase that seems to be quasi-universal. I don't know, how many people have been lost and felt a little bit kind of bad about it, Okay. So there is this concept, this feeling of being anxious of being lost. And in North America, it's called wood shock. This term was coined around the turn of the 19th to the 20th century when outdoor activities were getting popular. And people, when they would get lost in the woods, they would panic and start going in all sorts of directions and, of course, get themselves into a lot more trouble. But we aren't the only ones that happens to. Turns out the Vikings had won Hafila, which meant when they were at sea and they couldn't regain their bearings, they would have this anxiety at not being able to regain their bearings, and there's some examples in Norse sagas about that. In the Marshall Islands, you would think that the indigenous navigators would be incredibly good, but no, they would also get lost at sea, just like anybody else might get lost, except the might be somewhat worse consequences than getting lost in a parking lot. Their word was wee jet, and if somebody went out and got lost at sea and got wee jet, when they get back to one of their islands, they still would be a little off in the brain, according to one of my anthropologist friends. And recently, jet pilots who fly at very high altitudes and lose their sense of the horizon have something known as break-off phenomenon, where they feel that they're actually floating above their bodies, dissociated from the bodies. So there seems to be this universality of emotional responses of being lost, which suggests that not only is the wiring innate, but the responses to different scenarios is innate. So with that in mind, I'm going to zero in on a few specific cultures of navigation and talk about some very specific instances of how these groups found their way. And it's not that I'm talking about every way that they found their way, but just one or two specific traditions. Whoops. So the first group is an Inuit hunter-gatherer group known as the Netsilik, which is largely a linguistic distinction. They live in the barren lands to the northwest of the Hudson's Bay in an area called the Nunavut territory. And they're hunter-gatherers. And here you see one Netsilik who is trying to spear fish through a hole, which can be quite painstaking. Also, seals. So, for example, a hunter would have to stand over a hole with a spear, freezing, and waiting for that seal to show up, and at the right moment, pop the spear down. So it's a difficult life, made harder by the fact that these barren lands are flat. There are no trees in them. There's very little relief. So it makes it a real challenge to find your way, particularly if you're in a blizzard or something like that. Now, there was an ethnographer named Knut Rasmussen who did a survey of the islands in the Arctic archipelago of Canada and also along the northern coast of Alaska to try to look at Inuit culture before Western culture encroached on it. And the Netsilik were some of the most remote that he studied. And he was amazed at their ability to find their way through this barren landscape and didn't really know how they did it. But by way of probing, he would give them a pencil and paper. Now they weren't totally, they understood graphical representations, but they'd never seen pencils and papers before. And he asked them to draw their territory. And so from one of Knud's reports, here's a drawing by an Inuit hunter of what's called King William Land. These numbers are put in by Knut later on, and they could name a very large number of spots. They would have names for these different spots on these islands. So here's one, or Shuratuk, which means a place where one stamps one's feet. So presumably while you're waiting to spear the seals, your feet get cold, and then when you spear the seals, you get out and you stamp your feet. There would be another place like here, it's called the Nose for obvious reasons because it has it's this hook-like peninsula. Now the amazing thing is if you compare this map drawn by an Inuit hunter to a satellite image, you see pretty good scale between these two. And you see the geographic features reproduce reasonably well. This little hook nose here corresponds to that peninsula. These islands to the north correspond to these islands. This is in a spot called King William Island, which is considerable. It's about 70 miles across here. And you can see these little inlets here and so on. So they had in their brain a very detailed cognitive map of their environment. And the question then becomes, okay, you have this cognitive map. How do you find your way? It's flat. You have whiteout conditions. What do you use to orient yourself? Well, it turns out that wind was one of the ways of orienting themselves. And more than that, wind leaves a very distinctive imprint in the snow. So if you have wind blowing over powdered snow, over the course of time, you'll get ripples that have a long axis that's perpendicular to the wind direction. And you can tell by the shape of the ripples how old they are, how recently they were created. So imagine that you were traveling and you knew that the wind was blowing from the west for a certain amount of time, and all of a sudden the fog descends and the wind goes out. What are you going to do? Well, you know that the wind has basically encoded direction in these ripples, and you can follow them and maintain direction. Now, you can't maintain direction perfectly over some length of time. Your uncertainty in position starts to grow as you walk. But the idea is if you maintain position for some amount of time, you may come to a linear feature, like dog sled tracks that I'm indicating here. And so you maintain your direction, you come across dog sled tracks, and you can look at how deep they are, how much the snow's filled in, the depth of the dog prints and this sort of stuff, and then follow them to an encampment. So that was how the Netsilik, in broad brush terms, will find their way across the environment. So what they did was to take this complicated two-dimensional environment, break it down to finding a direction, and then finding a one-dimensional feature and following that. Okay? So I thought that was rather interesting how they did that. And then I had the good fortune to have a collaboration meeting in the Sahara and went in a camel out into the desert and slept overnight in the stars. And what did I see but ripples in the sand that were basically obeying the same behavior as the ripples that the Inuit saw in the snow. So here you see the prevailing wind directions and these ripples in the sand. But if you go to larger scale structures like dunes, they have this characteristic crescent shape, which also gives you some idea of the wind direction. So if you start to think about dunology and how the dunes, the wind shape of the dunes, you can start to use that as a way of finding the prevailing wind directions and finding your way. If you have questions about this right now, I can take one or two, but I think we're going to have time at the end for questions. Okay, so you all with me so far? Good. Okay, so I'm going to talk now, drill down to one topic associated with the Norse. There was this golden age of Norse sailing between about 800 and 1300 AD, which corresponds to a period known as the medieval warming period or the medieval climate anomaly. And this was a period when water temperatures in the North Atlantic became anomalously high. And some of the currents, for example, the current in the Strait of Denmark between Iceland and Greenland, reversed. And instead of getting flows from the north that brought ice down, you actually got flows of warm water from the North Atlantic, and this became relatively ice-free for this period, which aided in their expansion not only to Iceland, to Greenland, but then also briefly to North America. And the one archaeological dot that we have is this outpost, Las Omedo, at the tip of Newfoundland, which has some very interesting artifacts, longhouses, and even a foundry for making nails out of bog iron, which I found rather impressive. So during this medieval warm period, they would sail. A typical set of sailing directions would be to sail north along the coast of Norway until you found a geographic feature that corresponds to the latitude of your target destination. So you might have some latitude of a feature in Greenland that you want to sail to, so you sail north to this point in Norway, an island or a bay, and then you sail due west in what was called latitude sailing, and you try to maintain that latitude as long as you could until you bumped into your target destination. Now, some sailing directions would talk about passing through the Faroe Islands, between the Shetland and the Faroe Islands, and then as you cross the mid-Atlantic ridge, you would see an upwelling of nutrients. And there you would see a lot of whales and birds and fish milling around, so you knew that that was a kind of sea mark to tell you where you were, and then eventually you'd find your way to Greenland and then down if you wanted to go to North America. So what I'm going to do is talk a little bit about the use of the sun in Viking navigation. And I should note parenthetically that there was this interesting video that was done here at Harvard where 23 graduating seniors were interviewed at commencement, and they were asked the question, why is it warm in the summer and cold in the winter? And I'm not going to ask you to answer this question, but 21 out of 23 said that it's warm in the summer because we're closer to the sun and cold in the winter because we're further away from the sun. And yet, when you looked at this video footage of these seniors talking, the sun was high in the sky, the colors were bright, it was warm out, and you could even ask yourself the question, well, I could hold up my thumb at the end of my arm in the wintertime at the sun and do it at the same time in the summertime, and the size of the sun doesn't change, but it sure seems a lot brighter in the summertime, doesn't it? So you don't need, the quote-unquote right answer would be that the Earth's orbital axis is inclined to the orbital plane, okay, and then more of the northern hemisphere gets the sun in the summertime and less in the wintertime because it's angled. But the Vikings didn't know anything about orbital inclination or axial tilt or anything like that. The simple fact is that one knows, or should know, maybe we don't know because we haven't been paying attention, that in the wintertime the sun is very low in the sky, okay, and in the summertime it's very high in the sky. It rises due east at the equinoxes, sets due west at the equinoxes. It rises to the south of due east in the winter solstice and to the south of due west, sets to the south of due west in the winter solstice, and in the summer solstice it rises in the north to the north of east and sets to the north of west. And so here is what you would see for the arc of the sun over the course of the day, the solstices and the equinox in Boston. Now, it appears that the Vikings had some sense of latitude, the angle above the equator, and knitted that together with some sense of the position of the sun and how the position of the sun varied with seasons and also varied with our latitude. So just to give you an example, at the summer solstice, when the sun is at the highest angle in the sky in the northern hemisphere, here we have Boston, which was just this figure that I drew below. In Caracas, Venezuela, it actually arcs a little bit to the north of your zenith. And in Norway, Narvik, Norway, at 68 degrees north, which is just above the Arctic Circle, it never sets. So it basically orbits and goes around and never sets there. So if you just paid attention to the sun rather crudely in these places, you would have some sense of what your latitude might be. The length of day and latitude will conspire together to give you some idea of what you'll see at the summer solstice. So here is just a little plot of the length of day as a function of latitude at the summer solstice. So the length of day is longer in the northern hemisphere until you reach the Arctic Circle, where it's always 24 hours long. The sun never sets. And conversely, below the Antarctic Circle, you have no day at all. It's an eternal night. And of course, this is going to change over the course of the year. So here we go up to about 42 degrees where we live now, and you can see the length of the day is about 14 and a half hours long at the solstice. And as I said, you also have this rising of the sun that will vary with the date of the year. So at the equinox, it rises east, rises to the south of east at the winter solstice and to the north of east at the summer solstice. And this departure from due east is called the amplitude. So the maximum amplitude happens when you're at one of the solstices. So here is the maximum amplitude versus latitude. Right at the equator, it's about 23.45 degrees. We get up to the latitude of Boston, and it's about 32 degrees. And then as you go closer and closer to the Arctic Circle, the amplitude gets larger and larger until the thing never sets at all, basically. So you could use the rising and setting of the sun as a crude calendar. And in fact, when I told my parents about this, they have this little dining room that they have breakfast in, and it faces to the east, and there's this little woods and houses they can see, and they can see the rising sun projected against this, and they'll actually take a look, and depending on the time of the year, they'll say, oh, the sun's over there, so it must be January, or the sun's over here, it must be February. So here is a shot out of the porch from my house, and you can tell that it was not taken today because this house is just covered in icicles at the moment. But here's the setting position of the sun on October 21st. Here it is at February 21st, and here it is at March 2nd. And so I can actually use this as a kind of a crude way of telling date of the year. Okay, so now to the Norse. Now there are some artifacts that we have that suggest that they indeed use the sun to navigate. There is something called a sun compass that people believe have been excavated in Greenland. And there's also something strange called a sunstone, and I'm not going to go into those. But the one thing that we do have, we do know that the sagas are bona fide, written by people in Iceland at certain periods of time. So here is something that probably just looks like complete gibberish to you at the moment, but by the time I'm done, I hope you'll actually understand what it says and what it means, and it gives you some insight into how the Norse may have used the position of the sun to figure out where they were. So this is from the Saga of the Greenlanders, and in the Saga of the Greenlanders, the Norse go to this new land called Vineland, where they find these horrible natives called Skrellings who attack them. And they thought it would be a nice place to farm because it was kind of warm and so on. And there was this passage where the author seems to be trying to tell you something about the location of Vineland. So Mera var thar Jafendogri in a Grönlandi eta Islandi så hafti thar Ikarstad og Dagmalastad Skamdegi. Okay, so what the heck does that mean? Okay, so I'll try to decipher this for you. Because the sun was low in the sky, you could use it as a timekeeping implement, but it also could be a navigational implement in some way. So the Norse divided the sky, the horizon, into 8 pieces, and it was also a timekeeping way of keeping time. So when the sun was due north, that would be midnighti, which is midnight. Ota is at 3 a.m. when it's in the northeast, and it's due east, it's middermorgen. 6 a.m. Dagmal, daymeal at 9 a.m. when it's to the southeast. Hadegi, high day, when it's due south. Eikt, when it's at 3 p.m. Midafton, when it's due west. And Nattmal, night meal, at 9 p.m. when it's in the northwest. Now, frequently, if you lived on a farm in Iceland, you would use this to tell time, and you would associate positions on the ground with the position of the sun in the sky. So you might have a cairn or a mountain, and then this would get the name stad or place associated with it. So, I don't know, not Malastad would be a position to the northwest, which might correspond to a cairn or something like that. So Dagmalastad, here I'm starting to gain on this, is the position of the sun when it's in the southeast. And Eiktharstad is the position of the sun when it is in the southwest. So what this is saying here is Yafin Dogri basically means equal day. Yafin equal and Dogri means day. So in this place, in Vineland, the days were more equal than they were in Greenland and Iceland. Okay, so it's saying that the length of day, even in the middle of winter, is going to be about the same. Skamdegi means short days, so that is basically the winter solstice. So it said the sun passes from Eiktharstad to Dagmalastad in the short days. So it says that the sun is rising in the southeast and setting in the southwest. And so clearly the person who wrote this was taking some pains to basically specify the latitude in crude terms to the reader. And these Vikings also knew about Dublin, which would have been roughly at the same latitude as this spot. I better hurry up. Let's see. So here's another passage from saga of a group that went from Gardar in southern Greenland to this fjord that I won't pronounce up in northern Greenland, which is 70 degrees north. And they said that the sun shone both night and day. When it was in the south, it was only so high that if a man lay athwartships, that's across the vessel, the shadow of the gunwale nearest the sun fell on his face, but at midnight it was high as the home in the settlement when it is the northwest. So roughly speaking, what they're saying is that you could identify the latitude of this location as being quite distinct from Gardar, which is at 61 degrees north, and this fjord, which is at 70 degrees north, which is above the Arctic Circle. So again, they're trying to locate the position by identifying the position of the sun, the location of the sun. Okay, so you still with me, everybody? Okay. So in the equatorial Pacific, here's a map of it. We know that from archaeological data and also linguistic data that around 1600 BC, a group called the Lapita culture, Lapita people, started making sailings outside of sight of land, started making jumps through the Solomon Islands to the Santa Cruz Islands to Samoa to the Marquesas and Tahiti, and then around somewhere between 600 AD and 1000 AD started making jumps of 2,500 miles. And there was a certain hegemony of the Polynesians that lasted until about 1300, and then at that point the horizon of the Polynesians started to shrink. And so the first group that got cut off were the people of Easter Island that you can't even see down here. But if you're curious about finding about Easter Island, you might sign up for this little cruise. So what we do know now is ethnographers have looked at some of these island clusters, which have retained some of the indigenous navigational techniques, and one can speculate as to whether that represents well how people navigated back in the day when Polynesians had hegemony over this entire region. Some of the anthropologists I've worked with have noted that no one sign is infallible. You have to use many signs to find your way. So stars would be one way, winds would be another, swells would be another, and wave patterns would be another. So I'm going to focus on wave patterns in particular, but I'll just note this idea of a wind compass. Now remember, I told you that the Inuit used wind as a directional indicator. You can do the same thing when you're in the Central Pacific. In the period between April and October and November, roughly speaking, the winds blow out of the southeast and are quite regular. These are the trade winds and are accompanied by these clouds called trade wind cumulus clouds. It has this very distinctive shape associated with it. And in the island of Anuta, the name for southeast is Tonga. And so Tonga is both southeast, the trade winds, and this island cluster that exists to the southeast. That word does triple duty. In the period from November to April, the wind shifts around to the northwest, and so if you know something about the cloud formations and the time of year, you can do a pretty good job orienting yourself. Now, another thing that the wind does is it brings waves. It creates waves, and if the winds are regular out of the east, like the trades are, you're going to get swells that are going to be driven by the trade winds from the east to the west. Now, there were these mysterious objects that were found by or described by a German bureaucrat who goes by the name of Captain Winkler in the latter half of the 19th century. At first, he saw these things woven together that looked something like this and wondered what the heck they could be. And the islanders were very reluctant to speak about what these were. After gaining the trust of some of these islanders, it turns out that these stick charts were ways of navigating using wave patterns and how waves interacted with the islands and the marshes. So what I'm going to tell you a bit about is this gentleman here, Captain Corrent Joel, and the tradition of wave piloting in the Marshall Islands. He's been trying to revive this tradition. He learned wave piloting from his grandfather. And there are a number of other wave piloters in the Marshall Islands. An anthropologist who I've worked with, Joe Gens, has worked with Captain Corrent, and one of the things that I've been trying to do is to tease out some fact from fiction about the reports that he's been getting, because there have been some ambiguities in things that he's been seeing, and I think I'm starting to gain an understanding of what works in terms of wave piloting and not. So here you see Captain Corrent and a voyaging canoe that they used to test wave piloting. So here's one very simple example. So say we have this eastern swell driven by the trades. It encounters an atoll, and what will happen is it encounters the shallow waters around the atoll. It'll actually bend, so the refraction occurs as on the south side. The waves get bent to the north, and the waves that go around the north side of the island get bent to the south. And I can demonstrate this in a simple applet. This is just a representation where you'll see waves coming in from the right. The coloration is the depth of the water. This red line is a kind of a wall that represents the reflections. And you'll see the salient features of this. There we go. So here are the swells coming in from the east, and then they encounter the island and they start to refract around. Okay. And you get this crossing pattern in the lee of the island. Not only that, but you get some reflections back out into the oncoming swell. So you see a very distinctive pattern, and if you know what to look for, you can know where the islands are when you're as much as 50 miles out. And I'll just give you another simple example. You can imagine a situation where rather than getting refractions, you get a shadow in the lee of the island, but you also get reflected waves, and so here is basically the sum of these reflected waves and the swell interacting, and you can see you get these curious patterns that are sometimes referred to as knots, that are these I guess nodes, if you like, in the swells that go by the word kaj and rojip in the language of wave piloting. And then here you have the reflected swell coming back out that is moving in the same direction as the incoming swell, but 180 degrees off, and that goes by the name of Juranakme. So you can start to tease apart what's going on in these charts, and I'm not going to go through all of the details of this one, but this is a matang, which is kind of a teaching chart. It's like baby's first book of wave piloting. And what it represents is a fourfold possibilities of swells hitting from the four cardinal directions. There's a central island here, and then there are four islands that are represented at the ends of these crosses. And then these curved patterns are supposed to tell you something about how the waves interact with this island, along, sort of like what that applet was telling you previously, except we're playing the applet with swells coming from the east, and then in this case the west, and the north and the south. So here is one of the charts, stick charts that you'll actually see up in the exhibit, called a meadow. And rather than being a teaching chart for generally what happens with one island, it represents a specific region. So this is a cluster of islands in the south of the Marshalls. Here's Jalit, here. And here is this crossing pattern formed by the refraction of the waves around the atolls. And so this is meant to basically represent the incoming swells, these vertical lines here. These are some of the distortions that are possible, and then here's the actual interactions with the islands. So this is kind of an intermediate scale chart. And here is another chart that you'll see there, which, if you recall, there were these crossing lines here. This is in the southern part of the Marshall. So this is a large-scale chart of the Marshall Islands, and this corresponds to that same area, only to a different scale. So you can see the same pattern being repeated down here, but now this is all of the Marshalls by and large. And what's remarkable about this chart is that it is very much to scale. You can lay this on top of a map of the Marshalls and it would do rather well. So whoever built this had in their brains a cognitive map of the Marshalls. So one of the things I tried to do was to take that ripple applet and crank up the resolution as hard as I could go and see what sort of patterns emerged. And so I put in the outlines of all the islands in the Marshalls. You can take a look at this isolated one where you can see this crossing pattern in its lee, and then you could see these projections out for these interference patterns. And then you can also see these funny little tendrils that are connecting the islands, which corresponds to this mysterious phenomenon called drillib. Now, here's where some of the interesting problems arose from Captain Corinth. When Joe took him out on a test, he had some oceanographers that deployed wave buoys. The oceanographers also did computer studies of what the waves were doing on these islands. And Captain Corinth said, oh, I can see the reflected swells. But the wave buoys didn't see them, the computer simulations didn't see them, and nobody on board the vessel could see them. So what the hell was going on? He said he saw the swells, but nobody could detect them. Joe showed me a video of Captain Corinth looking at the reflected swells and told me something about the Marshallese that he used. And I'm a sea kayaker, so I could actually see the reflections. And what was happening was the reflected energy, the amplitude of the waves getting reflected back was much smaller than the incoming swells. And the oceanographers were all expecting to see the same height of the waves, and they weren't thinking in terms of having a very diminished set of swells. So somehow what was happening was Captain Corinth's I guess, pattern recognition apparatus was highly tuned to be able to see these weak reflected swells and was able to detect them. Unless you think that he was pulling the legs of Joe, he went down and took a nap, and Joe drove the vessel off to the southeast as hard as he could while he was napping, and then got a hold of Captain Corinth and said, okay, where's your home island of Arno? And nowhere to be seen, but he just said, oh, blah, 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 blah. Look at this interaction with this and this and this, and there's Arno out there. And it was dead on correct. So obviously he was able to do something. There was another person that Joe interviewed who didn't believe that you could have waves refracting around an island. And he was from the northern islands in the Marshall Chain, and said there's no way on Earth a wave could bend. And so there's just a shadow behind it. Turns out that in the island clusters he was in, there was shallow atoll shores, but a very steep drop-off underwater, such that you wouldn't realize any of these refractions. So he was basically generalizing from his own local knowledge of wave patterns and somehow thinking that that was universal, as opposed to the idea that there might be other things going on. So roughly speaking, I could come up with 3 cases where you have a wave shadow and no reflections, or you have a wave shadow with a steep drop-off underwater and a steep island cliff, and you get reflected waves that get reflected quite well. Or you might imagine a shallow atoll where the waves break, you don't get any reflections, but you get this gentle underwater slope that causes refraction. So all of these are possible depending on the bathymetry. So the question is, how do you understand what's going on in reality out there? What are these guys seeing if the reflections are really weak, and how do you start to tease it out? So what we've been doing is some computer simulations of waves to try to understand what the Marshall Island navigators are doing. And some of the best information comes from a paper where people deployed a sensor array off the coast of North Carolina. And I should mention that waves on the ocean are very difficult to model. you might think, well, waves are waves, and we study this in freshman physics and blah, 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 blah. Turns out waves on the ocean are by no stretch of the imagination easy, because you're talking about two fluids. You're talking about water, which is a fluid, and air, which is a fluid. And it is the air blowing over the water that creates the waves in the first place. And anybody who's done fluid dynamic simulations will tell you that doing fluid dynamic simulations for just one fluid is really tough. But doing it at the interface of two fluids is really, really tough. Doing it at the interface of two fluids and land is really, 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 really tough. So one of the things that I've been finding is that we have to rely on kind of multi-scale information to do adequate models for waves. So this was a study that was done off the Army Corps of Engineers testing facility. And I'll just give you roughly the results. So it takes a little while to understand this plot, but on the horizontal axis is the frequency of the incoming waves in cycles per second. So this little cluster here is at about a period of about 13 seconds. So you have swells that would appear every 13 seconds come in. And this is the angle in degrees of the waves traveling. So in this particular day, which was October 6, 1990, there was a hurricane called Hurricane Lily that was out in the Atlantic. And hurricanes produce very low frequency swells at predominantly at one single frequency. So here you see the incoming energy around 250 degrees, and here's the reflected energy, which is a lot smaller. But you also see this peak here at around 13 seconds for the period. So the solid line here indicates the incoming energy in the waves, and the dotted line represents the reflected energy in the waves. And what you can see is that the low frequency components are reflected much better than the high frequency components. And here's another day, 17th of November, 1990, where you have basically a lot of frequencies coming in, but only the low frequencies coming out. So what this suggests is that you want to look for the reflections in low frequencies and with a substantial reduction in the size of the swell. And so I'm starting in my mind to create a wave piloter's handbook, based on what I've been seeing. And as I go out on ferries and kayaking, I'm starting to notice things that I never noticed before about waves. And it's kind of the old adage that you don't know something's there until somebody points it out to you, and then all of a sudden you start seeing it. So we're still in the infancy of doing some of these tests, but there is a sophisticated model called SWAN, which is developed by a group from the University of Delft in the Netherlands. And here we're just looking at a simulation of wave reflections from a long barrier. This is at the same period of 13 seconds. Here's the incoming swell, and it's a long straight barrier which have very good reflection. And in fact, the reflections from the wall have almost no diminished size of the energy. So next we're going to try to look at slopes and see how well that tells us about how well we can reproduce the data from this study here. Okay, so finally, and I'm sorry I'm running a bit over, but I'll try to keep rolling. So there's an interesting story about the rise of Western celestial navigation, and I'm not going to pretend that I can give you all of this in just a few short minutes, but let's just intercept the trade routes in the Indian Ocean in the Middle Ages. The Arabs and the Chinese tended to dominate these routes coming from the Spice Islands, dropping off spices typically in Alexandria, and then the city-states of Venice and Genoa would dominate the routes in the Mediterranean. They would practice for these long jumps across the Arabian Sea and the Bay of Bengal, the same kind of latitude sailing that you might see that the Vikings practiced. But they didn't have the advantage of having the sun low in the sky, so the question is, what did they use? So one trick was the pole star. When you're at these latitudes, Polaris is only going to be about 10 or 15 degrees above the horizon. And so you can actually measure angles by holding out your hand. And at the end of an extended arm, my finger subtends about 1.5 degrees. Now, if you go into language, there actually is a word for that angle, and it's called an isaba. And so you could actually keep track of your latitude by how many fingers above the horizon the pole star was. Of course, humans are good at making instruments, so one of the earliest instruments that was used was something called a kamal, which basically was a plate that was at the end of a string that had a bunch of knots in it. So what you do is you find the right knot and you hold this out, and you can look at the height of the pole star as measured by the height of this little plaque, and use that as a way of maintaining your latitude. There are kindred devices that you'll see up on display. In addition to a kamal, there's one called a cross staff, which is a more sophisticated version of something that's doing roughly the same thing, but employed by Western European navigators. And here is I guess not the original map, but is a map that was based on a world map that was commissioned by Caliph al-Ma'mun, who was the Sultan of Baghdad for quite some time. He reproduced the measurement of the radius of the Earth, that was attributed to Eratosthenes. And this map, although you might not see it terribly well, you can see that there are lines that roughly correspond to longitude and lines that roughly correspond to latitude. And the language on the edge here is talking about something called a climb, C-L-I-M-E, which roughly speaking is a strip at more or less the same width of latitude where things are the same, where the length of day at the summer solstice is the same, for example. And this is a world map, and to guide you, this is the Mediterranean, the Arabian Peninsula. This is designated as India, and this bit here is the fabled Mountains of the Moon, which is the source of the Nile River. So, in the Middle Ages, the Arabs had tables of latitude and longitude. And what do you think they used the tables of latitude and longitude for? Well, it wasn't navigation. It turns out that there were two problems that they had to solve. One was figuring out how to face Mecca. So if you think about, everybody has to face Mecca in a great circle route. So now, when we think about longitude, all the lines of longitude converge at the North Pole. So if you wanted to pray to the North Pole, you would find a line of longitude and you would pray in that direction. Now, just rotate this around and imagine that Mecca is kind of a religious North Pole, and there's these lines of longitude that converge on Mecca. Then that would tell you how to pray properly to Mecca. So to do that, you need to know where Mecca is, and you need to know your latitude and longitude. So this was, in some sense, the utility for tables of latitude and longitude. And if you look at the accuracy of the tables of latitude and longitude, latitude was accurate to about a degree in these tables, typically. This is roughly speaking at the end of the 12th century. The supposition was that the shadow of sticks were used to measure the latitude at a given date of the year, which would be the equinox. So here is a little study I did when on vacation in Jamaica, where rather than reading spy novels, I put a stick in the ground and I took a bunch of little rocks and put them along the tip of the shadow at the equinox. Now it turns out on other days of the year, the path of the shadow of the stick is a hyperbola, which is a curved path, but on the equinox it's a straight line. And on that day, this angle here, the shadow, the shortest length of the shadow cast by that stick, this angle here gives you your latitude. So what I did was I put these little pebbles down, took a little string, measured the height of the stick and the length of the shortest length of the shadow, and I got my latitude to about a degree. So that worked reasonably well. I should mention that tangent tables used to be called shadow tables. Now here's another use for tables of latitude and longitude, and that's casting horoscopes. So most of you read in the newspaper your horoscope where you look down, I'm a Pisces, and I'm always at the end of the bottom of the page there. That's your sun sign. And that is this zodiacal sign where the sun was when you were born. But that's not all that is done in astrology. It's a question of where the other planets were in other zodiacal signs. But there's also something called a house system. And most people are unfamiliar with it unless you recall the song The Age of Aquarius, where you hear the moon, when the moon is in the 7th house, blah, blah, blah. So let me tell you that at the moment of your birth, at the place of your birth, there are these houses that encircle the sky, and there are 12 of them, like there are 12 zodiacal signs, and they correspond to different aspects of your life. So the eastern horizon, going down through the nadir to the western horizon, there are 6 houses, houses 1 through 6, and from the western horizon through the midheaven to the eastern horizon, there are another 6. So the 7th house corresponds to your spouse. I will tell you parenthetically that to learn something more about astrology, I did the astrological chart of a friend of my wife's. Safe to not do it of your wife. But she had Mars in her spouse house, and I would submit to you that having the god of war in your spouse house is probably not auspicious. But I did learn something about this. So, in order to do a horoscope, though, you would need to know the time and place of somebody's birth, their latitude and longitude, and then you would be able to predict what's up in the sky. So let's just turn this around and say, well, maybe I can reverse engineer the whole problem. And this is what was done first by the Portuguese. And the idea was that when they were sailing around the coast of Africa, at a certain point, they would cross the equator, and even before they crossed the equator, Polaris would get too low in the sky to be able to see, because you would get clouds and fuzz in the way and that sort of thing. So you had to go to other celestial objects, like the sun, for example. So the kings of Portugal employed astrologers, and so the very first voyages along the coast of Africa, astrologers would accompany the vessels with the tools of the trade, astrolabes and quadrants, some of which you'll see up in the exhibit, and also tables. You needed tables. So the idea is that now you know where things are in the sky, you know where they're supposed to be in the sky, and figure out where you are, as opposed to knowing where you are and figuring out where everything is in the sky. So here is a beautiful, one of the beautiful things we got from Houghton. It's an almanac by a person who put together these things called Regiomontanus. These in part were astronomical reports, but they also gave you astrological information. And this kind of looks like magic and gibberish, but it really isn't. And I'm almost done. So let me just tell you a little bit about what this represents. These are the positions of the sun, the moon, Saturn, Jupiter, and then if you go through the rest of the table, if you could look up stairs, you'll see Venus, Mars, and Mercury. And this gives you their positions. But it's in a funny coordinate system which we hardly use anymore. So let me explain this. So the sun will rise to the highest point in the sky at the summer solstice and the lowest point in the sky during the winter solstice. We look at it, the coordinates in the celestial sphere with a celestial equator, which orbits over our equator, a celestial north pole and a celestial south pole. And we have a kind of prime meridian in the sky that represents the zero, if you like, of what's equivalent to the celestial longitude. And that's when the vernal equinox occurs, and that's when the sun crosses the celestial equator, and that's the zero. So in the conventional scheme that was used in this day for giving locations, you would have 30 degrees of each of the zodiacal signs. So here you have Aries, Taurus, God help me, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, Sagittarius, Capricorn, Aquarius, and Pisces. For a physicist, you know. Okay, so the position of the planets and the sun were given as the number of degrees in each one of these signs. Okay, so you get somewhere between 0 and 30 degrees. So I will tell you that the sun moves in this plane of the ecliptic at about 1 degree per day, 365 degrees, 365 days in a year, so about a degree per day makes sense. So it's May. This is May 1488, which was the date when Bartholomew Diaz took a celestial sight to ascertain the latitude of the Cape of Good Hope off of Africa. And here is the sun. It is in Taurus, which is a good thing because it's May. And here you see it's at 20 degrees, 21 degrees, 22 degrees, 23 degrees, and so on. So it's moving at about the right speed. Here's the moon. It's in down here in Capricorn. And you can see 24 degrees of Capricorn, but whoop, and there it goes into Pisces, a couple days in Pisces, Aquarius. There is an Aquarius, a couple days into Aquarius, it goes into Pisces, and so on. So the moon is moving very quickly through the sky, and you can see that. Here's Saturn, and it's moving very slowly, and not only that, but it's moving backwards, so it's going in retrograde motion. And here is Jupiter, which is over here in Pisces, I guess, and it is moving forward very slowly, but the outer planets do move very slowly. So you can start to actually make sense of what's going on in this table if you know what the symbols are. This almanac was, a copy of this almanac was supposedly taken by Christopher Columbus on the voyages to the New World, and there was also eclipse information in there, and supposedly he used one of the eclipses predicted by Regiomontanus to find longitude on his 4th voyage when he was marooned in Jamaica. Okay, well, I've gone on way too long, but let me just sort of end, and I was just trying to follow the abstract. You know, we put together this abstract, and I had no idea, you know, what I was going to achieve in the end, so I was supposed to give you hints about what to do, and so these are the hints, and then I'll be done. So my things that I tell my kids, things that I tell my students, things that I tell people, like how can you improve your skills, how to stay found. So think about the landmarks you're going to expect along a route, and think about their permanence, which goes back to Eleanor McGuire's retrosplenial cortex. Something that people often don't do is look back at decision points. So whenever you come to a fork in the road, as Yogi Berra says, if you come to a fork in the road, take it. Well, look back. And the reason is that when you come to these decision points, if you don't look back, you don't know what it visually is going to look like when you reapproach it. And many people get lost because they just go off and not, you know, turn around and see visually what it is when you can't backtrack in that case. Note the wind direction. The wind direction is usually pretty solid over some period of time, and this has saved my bacon when I've gotten fogged in a kayak multiple times. The sun, if you start to pay attention to the sun, especially when it's close to the horizon, it will give you a good reference. How many hours is it before sunset? And if you know your latitude, you know roughly the path that it will take when it sets. Stars, in my class, students memorize 23 major navigational stars, and by about 3 weeks, they're able to orient themselves perfectly, tell you their latitude on the roof of the Science Center. You can see stars in Cambridge, by the way. On a given night, we could have students identify 15 major navigational stars right up here. And also the big picture. Try to not get seduced into having these little GPS units that all they're doing is tell you, turn right, turn left, and so on. But have a map, look at it, understand where you're going, and that sort of thing. So there you have a little sampler, and I hope you got something out of it, and I guess take questions. Okay. One or two questions. Okay, sorry. Yeah, I'm running. Sorry.
We can ask questions upstairs.
Yeah, I'll be milling around, so you can ask questions. Okay.
How did the Polynesians determine scale for their charts?
Oh, well, that's a good. A lot of times, the number of days. So, how do they determine scale in their charts? The number of days sailing, basically. So, there were in the Caroline Islands. There was a slightly different system that they used, but we can talk about that another time. It hasn't.
Is that related to distance?
Yeah, it was a way that they, in their mind's eye, were able to track their progress in a voyage from one place to another based on star compasses. It's complicated, I can explain. Yeah?
Is it apocryphal that there are gender differences in favorite strategies for wayfinding?
Boy, you aren't the first person to ask that question. I'm not aware of any, at least when I look at the students in my class and we have them do different tasks, I haven't seen huge gender differences, to tell you the truth.
The claim is that women favor landmarks.
Is that right?
I don't know. That's what
I have to ask Eleanor, because I know Eleanor did break it out into gender, so if there was some persistence of landmarks that she saw based on that, I can find out. So I'll ask Eleanor, just send her an email, and maybe we can exchange emails and I'll let you know. Yeah.
I just said to this question, when I was learning to fly small airplanes, I had this very gruff instructor who said, when I teach men how to fly, they try to calculate everything and they get lost. So the women, they find landmarks, and that's how you navigate.
So maybe there's some truth to that. I don't know. Yeah.
Great. Well, if we could thank John very much, and I hope everyone